Okay, we've been doing our Lewis structures, and hopefully you're getting pretty good at those. Don't worry, we're going to have a lot of practice at Lewis structures because the rest of this chapter and all of the next chapter depend on you drawing a correct Lewis structure to begin with. So everything is going to start with doing Lewis structures for the next chapter and a half. Let's look at another important part of Lewis structures, something called formal charge. And truthfully, the equation for formal charge, we'll go through it, but we'll find that's much more complicated than the actual concept of the formal charge. The formal charge on any atom in a Lewis structure, to calculate its formal charge, you take the number of valence electrons for that atom that you'd find on the periodic table. For example, carbon has 4 valence electrons according to the periodic table. You subtract from that the number of non-bonding electrons, the number of lone electrons in lone pairs, and then you subtract from that half the number of bonding electrons. So essentially what we're doing with this last part here is if there's a bond between the atom you're looking at and another atom, you kind of split that bond. One electron in the bond goes with the atom you're looking at, one electron on the bond goes with the other atom. Like I said, that's complicated. It's actually easier to do if we just look at an example here. Okay, here is nitric acid, the Lewis structure for HNO3, and let's look at the formal charge of each of these atoms. Let's start with the hydrogen. Note, hydrogen normally has 1 valence electron. There's no non-bonding, there's no lone pairs on hydrogen. And for a bond, we just kind of split that bond in half for formal charge. We're not actually splitting it, but we're pretending, okay, if we were to split that bond, 1 electron goes with hydrogen, 1 goes with this oxygen. So this hydrogen normally has 1 electron. Here's 1 electron from the bond. So 1 valence electron minus the 1 electron from the bond gives us 0. 1 minus 1 is 0. What we're saying is here this hydrogen has no formal charge. Let's look at this oxygen. Oxygen normally has 6 valence electrons. And, well, let's count the number of electrons around it for formal charge. 1, 2, 3, 4, 5, 6. Oh, oxygen normally has 6 valence electrons. Here's 6 electrons around it for a formal charge calculation. 6 minus 6 is 0. Note, very important here, if you're looking at octets, you count both electrons in the bond. If you're looking, does this oxygen have its octet? Well, yes, 1, 2, 3, 4, 5, 6, 7, 8. When you're calculating octets, you count both electrons in the bond. When you're calculating formal charge, you only count 1 electron per bond. So for formal charge, this is 1, 2, 3, 4 for the lone pairs, 5, 6 electrons. So oxygen normally has 6 electrons around it. An oxygen atom has 6 valence electrons. We count 6 for formal charge. 6 minus 6 is 0. No formal charge on this oxygen. Okay, let's go to the nitrogen. Nitrogen normally has 5 valence electrons. Let's count the electrons around here for formal charge. 1, 2, in a double bond, well, that's 2 bonds, so 1 electron from this part of the double bond, 1 electron from the other part of the double bond, gives us a total of 1, 2, 3, 4, 4 electrons. Well, nitrogen normally has 5 valence electrons. Subtract these 4 valence electrons, these 4 electrons here, and you find out we're missing 1. If we're missing 1 electron, we're missing a negative charge. That means 5 minus 4 gives us plus 1. So that nitrogen has a plus 1 formal charge. It's as if it is missing a valence electron that it should have. All right, note it still has its octet. This nitrogen has 1, 2, 3, 4, 5, 6, 7, 8. Still has its octet, but in terms of formal charge, 5 minus 4 is a plus 1 formal charge. Let's look at this oxygen up here. Recall oxygen has 6 valence electrons. We count 1, 2, 3, 4, 5, 6. We count 6 electrons around it for formal charge. 0 formal charge for this oxygen. So now let's look at this oxygen over here. 1, 2, 3, 4, 5, 6, 7. Ooh, recall oxygen normally has 6 valence electrons from the periodic table. 6 valence electrons minus 7 that we count means a -1 formal charge on that oxygen. So when we add it all together, we see this nitrogen has a +1 formal charge, this oxygen has a -1 formal charge, and all the other atoms have no formal charge. The deal with formal charge, a few things to remember. Your formal charges must add up to the overall charge of your molecule or ion. Note HNO3 has no overall charge. +1 and -1 cancel each other out, and so you added up these formal charges and we got no net formal charge on this molecule. That must occur always. The other thing to realize about formal charge, it's not an actual charge separation. When we were looking at actual charge, partial positive, partial negative, we have to look at electronegativity values. So this really isn't looking at the actual charge on the atom. However, what you're going to find, especially if you go into organic chemistry, is that the formal charge does give us a pretty solid idea of what part of the molecule does have more positive charge than you would think, what part has more negative charge than you would think, and it does tell us, we can use formal charge to tell us how organic molecules are going to react. The reactivity of organic molecules pretty much follows formal charge. It does a pretty good job of following the formal charges on things. So I feel it is very important to know how to do the formal charge, even though it's not really an exact charge, it's not really representing partial positive and partial negative. It will give us information in the future about how molecules react. Okay, so knowing that, let's look at carbon dioxide, CO2 2-, and let's draw it out, its Lewis structure, and figure out the formal charges that we would have. Alright, so let's see, CO2, what's the central atom? Well, there's only one carbon. Oh, actually, not CO2 2-, excuse me, CO3 2-, carbonate. There's one central atom. Carbon is the less electronegative, so I'm betting that carbon's in the middle and the 3 oxygens around the outside here. And when I count electrons, I count 24 electrons. Make sure I count that. Well, how did I get 24? Well, oxygen is 6 valence electrons times 3. 6 times 3 is 18. Carbon has 4 valence electrons, 19, 20, 21, 22. And we've got these 2 negative charges here, which means this has 2 extra electrons. 22 plus 2 is 24 electrons. So we need to put in the 24 electrons. I like to do it in one breath. Take a deep breath. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Boom. Got all 24 electrons in there now. Wait a minute. Does this carbon have its octet? The oxygens have their octet. The carbon does not have its octet. So what do we do if the carbon does not have its octet? That's right, we're going to take a lone pair from one of these oxygens, move it down to become a bonding pair, and that gives us this molecule there. Make sure we add in all of our electrons, and there we go. Alright, now carbon has its octet, everything is good. Now let's look at the formal charges. Well, where do you want to start? I'm going to start with this oxygen right here. Oxygen normally has 6 valence electrons. For counting electrons for formal charge, I count 1, 2, 3, 4, 5, 6, 7. 6 minus 7 means I've got a -1 formal charge on this oxygen. Now you could redo the count, but do you see how this oxygen and this oxygen are the same single bonded oxygen with 3 lone pairs? So we now know that this also has a negative formal charge because this and this look exact the same. Let's look at this oxygen up here. 1, 2, 3, 4, 5, 6. We count 6 electrons for determining valence or formal charge. We know oxygen normally has 6 electrons, so that tells us 0 formal charge on that oxygen that's double bonded. How about this carbon? Carbon normally has 4 valence electrons when counting formal charge. 1, 2, 3, 4. Well, 4 valence electrons for carbon minus 4 when we count for formal charge means this carbon has no formal charge, which means, wait a minute, I've got a negative formal charge and negative formal charge there. That's a 2 minus overall with our formal charges. Recall the formal charges must add up to the overall charge. So if I've got 2 minus here and my overall charge is 2 minus, that works. And because of this, when we're dealing with ions, when we draw these Lewis structures, what we're going to do is we're going to draw brackets around these guys and put my 2 minus on the outside. Because the truth of the matter is, even though I've got my negative formal charges on these 2 oxygens here, truthfully, the whole molecule, the whole ion of carbonate carries a 2 minus charge. It's a 2 negatively charged beast here. So we like to put in brackets to indicate, yeah, the whole thing carries a 2 negative charge, but our formal charges put a negative charge there and a negative charge there. What we're going to find pretty soon is our formal charges will be important also because we're going to find that sometimes more than one Lewis structure seems to follow the rules. I can draw 2 Lewis structures for a molecule. And so we find that some Lewis structures are just better than others. Some, well, this is more realistic. What makes a Lewis structure more realistic? One thing, octets. If every atom has an octet, that tends to be a better Lewis structure. The other thing to look at is your formal charge. We find that good Lewis structures, lower energy Lewis structures, more stable molecules, have lower formal charges. So if you can draw a Lewis structure that has 0 or plus or minus 1 formal charges, that's okay. If for the same molecule you've got plus 3 and minus 2 and all these larger number formal charges, that's probably not a very good Lewis structure. Nature doesn't like to have lots of positive and negative charge. Nature likes to neutralize things. Okay, and the last thing to look at, a good Lewis structure is probably going to have the negative formal charge. If you have to have formal charges, a negative formal charge on the more electronegative atom. Look at our carbonate up here. Oxygen is more electronegative than carbon, and we have a negative formal charge on this oxygen, a negative formal charge on that oxygen. The formal charges are on the more negative atoms, so that's a pretty good thing in terms of Lewis structure. All right, note, one could have, if one wanted to, and we can see this would be bad, have drawn the Lewis structure for oxygen just like this without giving the octet to the carbon. And if you did this, if you said, I'm just going to use carbonate, I'm just going to use this Lewis structure for carbonate. Well, that's not good, but let's look at it. If we did that, we will find, well, this oxygen has a negative 1 formal charge. This oxygen has a negative 1 formal charge. This oxygen has a negative 1 formal charge. Check out the carbon. Carbon has a plus 1 formal charge. And we look at that and we say, okay, what's wrong with this Lewis structure for carbonate? Why is this one so much better? Well, a few things. One, does this carbon have its octet? No, that carbon does not have its octet. So that's, better Lewis structures have all the atoms having octets. So that's not good. We can say this is not as good a Lewis structure because carbon does not have its octet. And look at the formal charges here. I've got 3 negative formal charges and a positive formal charge. Every atom has a formal charge. It's nicer to have fewer formal charges. Better Lewis structures have fewer formal charges. So instead of every atom having a formal charge, here only 2 atoms, our 2 electronegative atoms, have the negative formal charge. So that makes this a much better Lewis structure for carbonate than this. In fact, our whole idea, our whole rule is if the central atom does not have an octet, you form double bonds to do that, is because that gives you a much better Lewis structure. That's why that rule is in place. Okay, so but carbonate is an example of something, and here's another example of an interesting situation we have. Kind of a place where Lewis structures kind of break down. And I'm just going to end the video here because we're at 15 minutes. Because when we end up the chapter, we need to talk about these resonance structures, and we need to spend a little time on this. So I'm going to end the video here. We'll start up the next one with resonance structures.